Hello students, this video lecture is in continuation with the previous lecture where I have explained how to extract the various components of the currents based on instantaneous reactive power theory. To explain more on these lines, we are continuing with the same example. Okay, so if you see it here, that this on the right side of the page, okay, we are here. I will just put some cursor so that it is clear. So we are this part of this discussion. So this circuit we have studied previously, and based on the transformer action we have resolved the secondary voltage and current components, transformed back to the primary currents, and found there the active and reactive components. Now let us try to find out normal active and reactive powers using a standard phasor description. Okay, if you see the expressions of the currents on the primary side, you will say IA, IB, IC. Do you remember? We have found these expressions in the previous lecture. IA, IB, IC. IC is 0, IA is root 2 I sin omega t plus 30 degree. The phase shift has come because of the unbalanced load on the secondary side. Okay, secondary side, this is the unbalanced load here. So because of this we get these currents, and these are the voltage on the primary side. So these voltages and these currents can be used to find out the apparent powers, the active powers, and the reactive powers. Let us try. So this is the power computation, this part where we have found SA bar, complex apparent power in phase A, SB bar, complex apparent power in phase B and phase C. Here C is 0 because the current is 0. Alright, so this is BAIA conjugate. Substitute these values, you will get 19,837.5 watts, and this is 11,453.16 volt ampere reactives. The whole unit is volt ampere. If you want to explain in terms of the active power, reactive power, it is watts and the volt ampere reactives. Similarly, SB is 19,837.5 plus J, same amount. Now except the polarity, okay, except the polarity, others are same. So you see this is minus J and this is plus J, okay, and that makes the reactive power equal and opposite. And if you sum them, then you can see that the overall reactive power is nothing but the equal to 0, and P is nothing but PA same as PB, as you can see from these two values. Okay, so this makes 39,675 watts of power, and there is no net reactive power. That is in line with our guess because there is no net reactive element on the load side. So obviously there will not be any reactive component, there is no reactive power from the source. However, the source phases are experiencing reactive powers. Okay, the source phases are experiencing reactive power because of the unbalance which has got some phase shift with respect to their voltages. Fine. So overall we can say the three-phase reactive power is equal to 0, the net reactive power, and three-phase active power equal to twice of each phase power, that is PA or PV because they are same. That is the 39,675 watts. This is fine, and based on that we can also compute secondary side as well. We can find VA conjugate. Secondary side IV equal to 0, IC equal to 0, and therefore the SA bar is root 3 times of B 30 degree because current is root 3 times of B, angle phase shift 30 degree. Okay, and this becomes this is voltages, which is basically line to line voltage, and this is the current, and the power is this much. So you can see the secondary side real power is same as primary side real power, and secondary side reactive power is same as primary side reactive power. Alright, but in between what happens? In between the phases are being involved, and because of that there is a power factor in each phase. In fact, the phase A experiencing as 30 degree phase lead, and phase B is experiencing 30 degree phase lag. Hence they form equal and opposite reactive powers whose summation is equal to 0. And this is earlier concept that we can find out, therefore based on this the different apparent powers and the power factors calculation based on them. For example, this is the SB, this is S arithmetic, this is S effective. Okay, so this is mod of SA bar plus SB bar plus SC bar, which is 39,675, and arithmetic is mod of each apparent power, which is 43,813 bars, and S effective is 3 into V effective and I effective, which becomes 3 into 230, and IA square plus IB square plus IC square plus IN square by 3. These two are 0. Okay, these two are 0. The remaining is this power, and the remaining is this power, which makes the 2IA square. Substitute value of IA, we will get the S effective as 56,116.27 volts amps. This is the dimension is actually volt amps. Volt amps. Now these are all volt amps, so you can correct them. This is not a bar actually, this is a also volt amp. This is in watts because there is no reactive component, so you can say volt amp same as watts here. Now based on this we compute the power factors. Okay, so you can see the power factors, basically this is power factor phase B, and this is power factor phase C, and so on. Okay, this is power factor phase C, and then power factor of phase effective. Okay, so this is power factor effective here. So effective is PY as effective, and you can see this is actually power factor unity. This is 0.866, this is 0.707, and obviously as I explained in my previous classes that from design point of view we shall prefer to use the power factor effective because it gives the most pessimistic case, the least value of power factor, which results in a proper design of the feeder. Okay, that is one point which have been explained in the previous lectures, the last unit in fact. Okay, all this is fine. How to correlate the previous study of various components of currents like active and reactive components of current to the standard notation of the active and reactive components of current. How do you find directly the active and the reactive components of the current for a given voltage and current in a circuit? For example, in this particular case, we have three phase voltages as this. This is the BA, let us say phase A, and this is phase B. Okay, this is the phasor diagram for this. This is a phasor diagram. Okay, so phasor diagram is here. Now this diagram shows that the current I leads the voltage. Therefore, the phase angle between the current and the voltage is 30 degree, and hence we can write this is IA phasor. Okay, so this is IA phasor, and this is the IA phasor, this is the current phasor. So it has two parts, one is the real part, another is the imaginary part. So this is the real part and this is the imaginary part, which makes root 3 by 2I plus ji by 2. So obviously the real part I will denote by term IAR and the imaginary part by IAX. X for imaginary and R for real. Therefore, we can write the IA, the real part, will be in phase with the respective voltage. For example, this component, if I resolve along this component, okay, here, if I resolve this along with this, okay, so then it will be in phase with voltage. So this active part is in phase, the real part of the current is in phase with the voltage. Therefore, we can write that this is the real part of the current with a magnitude of root 2 is the factor for the peak value, and root 3 by 2I is the value of this I cos 30. So this into sin omega t. And what will be the reactive component? The reactive component will be root 2 times of the RMS value of the reactive component into sine of omega t plus 90 degree. Because this current will be the 90 degree along this component. So this current, this component is here. Am I correct? This is here. And hence the expression for the reactive component of current will be root 2, root 3 by 2I here, root 2I by 2 sine omega t plus 30 degree. This is the reactive component of current. And this is the active component of current. Obviously, if I sum them, the active and reactive components, their sum must be equal to IA. Is it correct? Should I check it back? You can try it. Okay. So we are trying it here. This portion. Okay. We are here now. This portion. We are adding IA active here and IA passive. By adding these two, root 3I is root 2I is common, root 3 by 2 sin omega t plus half sin omega t plus 30 degree. Either you can expand in time domain and simplify them, or you can use the phasor techniques to simplify them. So this is simpler because sine omega t plus 90 degrees, so I can expand into sine and cos. So it becomes half sine omega t cos 90 plus half cos omega t sine 90. This becomes 0, okay? And the next becomes half cos omega t plus sine 90. Sine 90 is 1, and therefore B finally get this expression, which is same as earlier expression. Clear? So these are standard definition of the active and reactive components. It gives me back the same amount of current which was flowing in the A phase. So A phase has a active components and reactive component. Now what about phase B? The same way we can analyze the phase B. This part we are studying phase B here, okay? So here onwards we are discussing the phase B. In phase B, this is the voltage, this is the current, and therefore this is the IB. So IB is minus 30 degree actually. Now there are two ways we can think about this. One is having the absolute angle of the current. Second thing is I have to observe this current with respect to phase B voltage. Like previously we have observed phase A current with respect to phase A voltage. Similarly, we should observe phase B current with respect to phase B voltage. Then I have idea about what it forms the active and reactive components of the power, as well as the active and reactive components of current with respect to phase B. Okay, so if you observe here, if I say that my phase B is the reference, so I will make minus 120 as the standard phase. So minus 20 will act as a basically 0, because phase B, if I take phase B like this is phase, suppose this is, I have a phase B here, this is suppose BB, okay, I'm sorry, this I must avoid this, take a standard line here. So okay, and this is the current here. So this is the current. The current is minus 30 lag. This is IB. So we can call this BB as a reference phasor. In that case, this angle is minus 30 degree. Now again it has two components, like this and like this. So one is the real component, another is the phase quadrature component. This time this component is negative because of minus 30 degree. Okay, so I have denoted this IB as IB dash. This IB dash is the phase B current with respect to B phase voltage taken as a reference. That's why IB dash, we have used the term IB dash. Okay, so IB dash is basically I angle of minus 120 degree, which is in phase with the voltage of phase B, and therefore we can again transform into their active and reactive components. So IB dash cos 30 becomes this phase, and IB dash sin 30 with minus sign becomes this, and they form the real part and the imaginary part, and they finally lead to this value and this value. Okay, now if you look in a similar fashion, then IB dash active basically means the active component of V phase current with respect to phase B voltage is this one, and the reactive component of phase B current with respect to phase B becomes this one. So therefore, finally we have phase B active this expression and phase B reactive is this expression. Okay, if I observe with respect to 0 axis, A phase axis, so I will add one extra minus 120. Is that clear? This is very important step. It must be clear how to express them with respect to phase B and this with respect to phase A. Correct? Fine. But thing is that when we want to observe its active and reactive components, they are in respect of the active and reactive powers, and active and reactive powers are being formed with the relative angle between the voltage and current, and therefore we need to observe these current components of phase B with respect to phase B only. Alright, with respect to phase B only. Now you see that particular thing, that if we observe these two currents simultaneously, four currents, IA active, IV reactive, and IA reactive and IV reactive, then we see a very important characteristic. What is that? The important characteristic is that the sum of IA reactive plus IV reactive equal to 0. You see it here, negative sign. IV is by magnitude it is same as the IA because this is kind of a RMS value, and this is negative sign. So if we add this IV dash reactive with IA reactive here, okay, these two, you see the sign is the same as I actually. So basically this becomes minus I. Alright, this IV is same as minus I. So I can just circle this. This is same as I. And hence the summation of these two components of currents, that is the IA reactive plus IV reactive equal to 0, and IA active, if you see, and IV reactive, then they are same. You can see it here. So IA active is root 3 because this is same as IV, this is same as I, and this is IA active, this is IV active, both are same. This is standard resolution of active and reactive components of the current in any phase of the system. And similarly we can find for phase C, if this is a phase C, but right now the current in phase C equal to 0, and therefore the phase C current components are 0. Now we come to very important point. What is the relationship between these standard resolution of active and reactive components with the active and reactive components being resolved based on instantaneous reactive power theory, these ones? So what is the relationship between these and these two? Are they same or they are different? There is no connection between them. Our common sense tells that if the theory is in line with the standard definitions of active reactive powers, okay, in that case they must be same. If this is doing something else, okay, then it is a different phenomena. But right now we see in this particular case IA active plus IV active, they are same and their value is this much. Here if you see IA active, IAP and IBP, if we sum them, this is not equal to 0. this is not equal to 0. Similarly, this is not equal to, or this is not, they are not equal to same actually. Like here if you see IA active and IV reactive are same in this particular case. Okay, this condition. But here this is not true. This condition is saying that the IV active and I active are same, but this condition telling they are not same, they are different. Also, the sum of IA reactive and IV reactive equal to 0, but here if we sum them, they are not equal to 0. If we sum these two, they are not equal to 0. So that's, I have asked question here, are there common things are there between these two expressions? The answer is no. Then the question arises that what PQ theory or instantaneous reactive power theory resolves is one way misleading conceptually to resolve the component in terms of active and reactive components. It won't agree with the standard convention of the reactive and active components of the current. To verify further, we will do one more thing. Okay, we just find out what is the summation of P active and P reactive. If we sum the two components, total P active is sum of P active plus P reactive, which is PBA into IA active plus BB into IV active. If we multiply these two, you can see it here, root 2b sin omega t into root 2 root 3 by 2 by sin omega t, and another phase is this. Okay, then we get two components. Sin square omega t becomes 1 minus cos omega t by 2. Root 2 and root 2 will go with this thing. Okay, this will go with this 2 term will go with this, and sin omega t, I will make it sin square omega t becomes 1 minus cos omega t by 2. Okay, this 2 and this 2 comes from the sin square omega t term. Similarly, this 2 and this comes from the cos square sin square omega t minus 120 degree. Okay, and if we find out its average value, the average value of the P active, then it is called P active bar. It is root 3b into I, because this average value becomes 0, this value is 0, and its average value is 0. So it becomes nothing but root 3b into I, and I is root 3 by r, root 3b by r becomes 3b square r. This is what we have calculated a long time back, if you recall our previous discussion. Okay, and most interesting part of this study is that if we find out A phase instantaneous power here, okay, if we find out this power, which is nothing but BA into IA, now I can write this is BA into I active plus IA reactive, because IA has two parts. Okay, this IA has two parts, IA active and IA reactive. So I will multiply each with the voltage. So BA into IA, this part, and BA into IA reactive, which becomes actually PA active and PA reactive. That's how we define. When we started this course in single phase unit, this is the first thing we have defined, the active and reactive components of the power. Okay, now if we substitute back into this, so root 3b into sin omega t into root 2i cos phi sin omega t. Now this I cos phi is the real part of the I. You can see from this side. Okay, if you go here, then you can see that this discussion is about that. What is this? It says, let us say IA in general be root 2 into I into sin omega t minus phi, this term. Okay, so in general you may have this kind of expression, which we can resolve into the real and imaginary part. So in phasor we can denote this by I angle of minus phi So become I cos phi plus j minus I sin phi, which becomes the real part, is become imaginary part, and therefore IAR is IA active, which is root 2 into I cos phi sin omega t. Sin omega t is a term which shows that IA is in phase with the voltages, A phase voltage. Similarly, IA reactive is nothing but root 2 into minus I sin phi, because minus sin I phi is the reactive component of the current, into sin omega t plus 90 degree. Okay. Now, if we use this substitute bracket here in general for any current expression, then you will see this becomes I root 2 I cos phi sin omega t. This is root 2 minus I sin omega t plus phi. You multiply them back, then we will get these expressions. Okay, and what are these? These are nothing but product of B into I. These are nothing but the product of BA into IA. Okay, where BA is any expression, let us say root B sin omega t, and IA in general could be root 2 into I sin omega t minus phi. Just I taken this expression. Okay, this is minus phi. Okay, if you multiply them, you will get these two resolutions, and which be in the beginning we have defined them as the active component and the reactive component. This is the total power P. Okay, this is the total power P here. So this is P function of time equal to P active plus P reactive, and P active is Bi cos phi 1 minus cos 2 omega t minus Bi sin phi sin 2 omega t. This was the first discussion we have started this course, single phase system. And now you have an answer why this is called Bi cos phi 1 minus cos 2 omega t as P active, and minus sin 2 omega t as into minus Bi sin phi as a P reactive. The idea has come from its active and reactive component of the current. If you have two elements, let us say R and X, in a series circuit, then this power is associated with the resistive element, and this power is associated with the reactive element. This is also meaning of the same expression. Okay. So I hope that you have fairly good understanding of these terms of the active and reactive components of the current, as well as the powers and the resolutions using the standard notations, as well as using the instantaneous reactive power theory. Okay. Similar example is also given in the book in section 5.2, where we have connected the inductive elements. The other concepts are same. Whatever I have explained for the resistive load is true for inductive load. Only the nature of power will change, the nature of current component will change. For example, it is now reactive element, so there should not be any active component of the currents, and the summation of the active components must be equal to 0. Okay. So I leave this as a tutorial for you, as a assignment or as a self-study. Go through the section 5.2, example 5.2, and study it. In the next lecture, I will start with the new control algorithm, a new discussion that is called as instantaneous symmetrical component theory. Okay? All right. So we shall meet in the next lecture, maybe in a couple of days. I am also planning to have tomorrow as a basically Zoom meeting or some Google Hangout. So I will send message to you through email, and accordingly we will plan it. All right. Okay, then I'll stop here.